Hi everyone. Today we're going to be working our way through kind of a different day. I want you to kind of picture today to be a bit of a problem-solving day. So what we're going to look at is some problems that are going to have some nuance to them or some subtleties to them. Maybe some multiple routes through to be able to solve. But we're going to be moving away from kind of your standard measurement problems, and we're going to work into some with a little more complexity. So, what I want you to do today is to tackle all of these problems on your own. And we're only going to walk through the first problem together. If that means you're reaching out to friends to try to stumble your way through some problems, do so. Okay, I want you to give the first problem a read. And just for the sake of us all being uniform, I want to talk about what we're going to address when we say that we're going to cover this cake with icing. That means that we're going to cover the surfaces of that cake with icing. But again, let's make sure this is just for uniformity. We are not going to have, so there is no icing in between the layers. I know that a lot of cakes have icing in between their layers. We're not going to put any in between these for the matter so we can discuss some things. Lastly, we're not going to have any icing on the bottom either. That one I think we would all agree with. So, what I want you to do is to try to figure out how many square centimeters of icing are going to be required to cover all the surfaces of that cake. So if you want to think of it this way, the surfaces you can see. No icing between the layers, no icing on the bottom. So let's pause the video now. You work your way through and we'll see if we match up. Okay, we should be back. So I want to walk through maybe a couple ways to deal with this. And what we're going to do is we're going to maybe just kind of build up a little bit. So I'm going to try to highlight the cake with as many colors as possible. And then that way we can maybe see all the different surfaces that we're going to have to cover. Well, I think that we can see that we're going to first have to put some icing maybe on the top. And so I'm talking about the area of that circle. And I know that the area of a circle is pi r squared. So I'm talking about pi, and my radius in this instance would be 5. And so I have 25 pi centimeters squared for the top. Now you don't need to put your units on there because that's not a final answer. And we're going to continue to work our way through. Okay. Well, now maybe what I need to do is I need to put some icing on that lateral surface, the top layer. Okay, that lateral surface, we know that if you went through and you folded that out, would be a rectangle. And so it's a 2 pi r for the length of that rectangle times h. So I'm calculating then 2 pi, and I need to now use the radius of 5 along with a height of 5. Okay, so that's going to be a 50 pi centimeters squared. And I'm going to continue to build. Well, the next easiest one to be able to deal with would be this lateral surface on the bottom tier. And so that would be a rectangle as well with that same 2 pi r h. So I'm talking about then 2 pi, the radius of that bottom tier, it has a diameter of 20, so it's a radius of 10, and a height of 10. And so I can simplify that to 200 pi centimeters squared. Okay, and now we're left with what I'm going to highlight in yellow. And it's that ring that we see. that's the top of the bottom tier, but outside of the top tier. And if we were going to work our way through to try to deal with that, maybe we could see two things. That we could see that it would be the entire bottom, and then what we need to get rid of is that top. And when we do that, it would leave us with that gold ring. So for me to go through and calculate just that ring, that means that I'm going to need to deal with a circle, subtract a circle. So the first thing maybe then that I focus in on is going to be going through and calculating the area of that ring. Okay, so it would be the entire top of the bottom tier. And that's a pi r squared, the area of a circle. And the radius of that bottom is 10. But I now need to subtract that orange circle from the top. I need to subtract the top tier. So that's a circle. That was pi times radius squared. Okay, so if I just continued on to calculate that, that would be 100 pi minus my 25 pi, and there's 75 pi. Okay, for us to get our total area then, we need to go through and we need to add up all of that stuff. So my area in total is going to be my 25 pi for the top, add on the 50 pi to finish off the top. There's all the surfaces of the top tier. Add on to that the bottom lateral surface and the ring on top. And if we do some quick calculation, we've got 100, 300, 350 pi. Now, there is your exact value. Question asks how many square centimeters. You are okay to put on that and give a perfect answer. However, we don't talk about it that way. And so we're going to go through then and we're going to turn that into an approximate. And so when we get an approximate to that, there's my approximate symbol, 1099.56 centimeters squared. And there we go. So you take a look at that solution, and that would be what I would argue is the most straightforward way to be able to go through. Not the maybe most efficient way to do it, but the most straightforward. Take each section in its bits, consider what that shape would be, and slowly build your way as you work your way through. Okay, what I would like to do is I would like to take a look at a part of that problem and see that we could actually simplify some stuff. And what I want to actually draw your attention to is this diagram that I drew pretty crudely. I'm going to just get rid of that diagram for a second, and we're going to blow it up in the middle, just so that we can maybe see that there is a faster route through here. And what I'm talking about with that faster route is actually a combination of these two steps. What I'd like you to imagine, like maybe imagine that that cake is sitting on the floor, and you have the ability to stand directly over that cake and look straight down. Not looking down on an angle, but looking straight down. What surface do you see? Well, you're going to see the top circle. That top circle on the diagram that I was given was labeled in orange. You're then going to see the bottom ring. You'll see outside the top circle I want you to notice that if you stood directly over the top of that cake and looked down, you would really see one circle. You wouldn't see it as two layers. The one circle you would see would be the top of the bottom layer. And so what we could do then is we could just calculate the area of that circle, the top of the bottom, using pi r squared, and you would get your 100 pi. Notice that is these two parts put together. And so I could have avoided, and I'm just going to put a little line through here, having to deal with the ring if I just looked at all the horizontal surfaces coming together to form a circle. I still would have had to find the lateral surface of the top, the lateral surface of the bottom, but I could have just done one calculation and found that full circle. A way to make your solution a little more efficient. Okay, there's a couple of the ways through the problem. Now, your job is to jump in and work through the rest. Work your way through the bowl problem, see what you can come up with, and then on the second page, work your way through the pool. There's going to be some little nuances, as I said, some subtleties, some things that we're going to have to examine and make sure that we include. So today is going to feel like a problem-solving day. This day is going to challenge you to make sure that you've considered everything. Best of luck. Okay, so what we're going to end up doing is then just looking through the rest of these solutions to question 2 and 3. As I said earlier, you've already reached out to people if you needed to. We treated this like a problem-solving day. You've gone through and stumbled your way through. All we're doing now is we're just confirming our solutions or maybe seeing some of those little intricacies that we may have missed. So what I'm going to do is just shrink that down a little bit. We have our page in front of us, and now we should be able to go through and come up with a solution to this bowl question. So we take a look, and hopefully we can see that that bowl is made up of 3 parts. That we're going to have to cover this in lacquer, so it's like we're painting it. I'm going to have to cover the outside of the bowl. And so the area of that outside, and I'm just going to like draw my little shape. That's my half of a sphere, demisphere, is going to be that area formula, 4 pi r squared, now cut in half. Okay, now I'm also going to have the inside that I'm going to have to cover, and that's going to be another sphere. So I'm also going to have this other sphere, or half sphere, that I need to calculate the area of, and I've got that same relationship. So for us to be able to go through pretty quickly, maybe we divided out the 4 divided by 2 and shrunk that down to 2. We have our pi. When we look on the outside of the bowl, outside edge to outside edge is 14 centimeters. That means that our radius is 7. And so now when I go through and I calculate that, I'm going to have my 7 squared, which is 49. 49 times 2. There is my 98 pi centimeters squared. So that gets me the area of the outside part of the bowl. Now I could do the same thing and get the area of the inside of the bowl. I can divide out my 2. I have my pi. The inside is 12 to inside edge to inside edge is 12, so that's going to give me a radius of 6. So that's going to be 36 times 2, 72 pi. So if I was to take those parts, then I could go through and I could work that total area. Now, the part that I think is the most common one for us to forget would be and you see me shading it in red right now, we need to make sure that we put lacquer on that rim, so the ring around the top. Now, how would I calculate the area? And I'm just going to draw like a little ring. Well, we tackled that one on a previous day. That's a two-dimensional shape, and it is a circle on the outside. We're all good that the area of our circle is pi r squared. So I'm going to have the outside circle, which is a pi with a radius of 7, and then I need to subtract my inside circle, which has a radius of 6. So if I do my calculation, I'm going to have 49 pi minus 36 pi, and that's going to get me 13 pi. So the best possible answer we could come up with then would be to say that the area of the total is going to have to be my 98 pi plus my 72 pi plus my 13 pi, and now we can add all that up. So when we take our 98 and add on our 72 and then our 13, that's going to get us up to a total of 183 pi centimeters squared. Nice. Now, if you take a look back into the question, it never asks us to come up with the area, and therefore we don't need to give this perfect value. So I'm going to go back, and I'm going to allow us to go through and work with some estimates. However, if you got down to 183 pi, that is great. It's not the answer we have yet, but that is great. Okay, I'm just going to get rid of that part because I would have had a bunch of people that would have wanted to deal with approximates in each one. Like maybe we came up with the area on the outside of the bowl was 307.88 centimeters squared. The area on the inside of the bowl was 226.19 centimeters squared. You see all my approximate signs. And the area of the rim was 40.84 centimeters squared. And so maybe then we would just say, well, then the area of the total is all of that stuff added up. And so, yes, this is probably a calculator issue for us, and I know that that's okay. And that's going to get us a total area of 574.91 centimeters squared. And there we go. So if we work our way through, we can come down to that, and that gets us pretty exact. It's pretty close. Okay, I'm going to highlight a couple things in the question. The first thing that says is we're looking to make 25 bowls. So as soon as we make that calculation, then we need to make sure that our total, that our total area then, not of one bowl, but of the 25 bowls, is going to work out to 14,372.75 centimeters squared. There is us coming up with, and actually let me just get rid of that highlight. I want to put that in green. That was our calculation to take into account the 25 bowls. Now we read further into the problem, and it tells us that 1 tin of lacquer covers 1,200 centimeters squared. So what we need to do then is to take that green value, and I'm just going to scroll up right now, and we need to now determine our amount of lacquer is going to be that 14,372.75 divided by 1,200. When I divide that by 1,200, I get 11.98. Now, this is very important for us. Can we buy 0.98 of a tin? Probably not. If we're going to buy like a can of paint, a can of lacquer, then we have to buy the can, or we don't buy the can, but we don't get to buy part of the can. And so hopefully then we're good that we would round that off to 12 tins. Now, before I have anybody who goes, well, yeah, of course, because you would round 11.98 off to 12, be very careful. If our answer was 11.08 instead of 0.98, we would still have to round that off to 12 tins because 11 wouldn't be enough. Okay, so hopefully we worked our way down to that, and we found out that we need 12 tins of lacquer. So if I scroll back down just to be able to see the problem, the last part that I'm going to highlight in red. Each one costs $4.98. And so if I then take that value, I need my 12 tins, $4.98 per tin. And that's going to give us a total cost of $59.76. Now, the question doesn't say anything about tax, so we'll finish it off there. Nice. So hopefully we were able to match up with that solution in the end, and we can see how we got there through all that solution you see on the screen. Nice. Okay, let's jump over onto the next page, and we'll work through that swimming pool. Okay, so what we see in that diagram, it says in the problem, there's our cross section of an in-ground swimming pool. So imagining that we were able to dig down beside the pool and look at it from the side. What problem A asks us to deal with is to determine how many liters of water does the pool hold. And we have a little extra information given on the end, just if we were unaware, how to take meters and turn it into liters. Okay. Again, this is just confirmation of the solution you've already come up with. So I look at that swimming pool and I recognize I do not have a formula for that thing. So I want to try to break it up into regular shapes. And I think the easiest way to break it up is to imagine that this shallow end comes out a little bit farther. That where we see the slant from the shallow end to the deep end, if it came all the way until we get to the deep end, then if we were to divide up that shape, that you might actually now see 3 shapes that could make up that entire pool. So I'm going to go through and I'm going to label them. We're going to deal with some colors in it as well. That really what I have is this really, really thin rectangular prism. And you can see that green portion that's represented up top. Then what I'm going to have is I'm going to have this yellow triangular prism that's going to exist down here. So the green and the blue are the green and the gold are kind of fighting each other right now, but we can at least kind of see it a little bit. And then we'll just leave the big deep end box until the end. So if I was to go through, I could label all of those as box 1, triangular prism 2, and then box 3. Okay, for me to work my way through then, let's jump into box 1. So I'm going to calculate the volume since I want to know how much does something hold, that is the space inside a 3D object. And shape 1 is just a box, so I know it's length times width times height. And so I need to figure out the length of that box. Well, that means that I really need to figure out how long is it in that extra little portion that I just put on my diagram. This is going to require us to look up at the top of the diagram and notice that the pool is 9 meters long. We know the shallow end is 4 meters long, and we know the deep end is 3 meters long. So we should be able to tell that to transition from the shallow end to the deep end, the slope, and I don't like that last arrow I drew, must be 2 meters. The 4 plus the 3 gives me 7. I need 2 more meters to get up to my total of 9. And so my length is going to be the 4 plus the 2, so 6 meters. My width is going to be how wide the pool is. And my height is going to be how deep is that pool, 1 meter. So that box 1 gets me 30 meters cubed. If I now take a look at my yellow triangular prism, that box 2, well, I know that I can calculate the volume of that as base times height divided by 2, the area of the triangle, multiply that by the length of that prism. And so I've got my base, which was 2 meters, times, well, my height. Well, I'm going to have to figure out what that height is. Well, the total height or depth of the pool is 3. My shallow end is 1. And so therefore, the height of that prism must be 2. And now it's 5 meters deep. And so I get a 4 divided by 2, which is 2. 2 times 5, there is my 10, and my 10 meters cubed. The only thing left to find is our deep end. And the deep end is one big box. And so if I find the volume of shape 3, that's another length times width times height. And that's going to give us 3 by 5 by 3. And there is a 45 meters cubed. And so to finish that whole thing off, then we should be able to say that the volume of the total is going to have to be my 35 plus my 45 plus my 10. There is 85 meters cubed. Nice. Okay, what does the question actually ask us, though? It says, how many liters of water does it hold? So we could then say, therefore, it has to be 85,000 liters. Notice what we have up there in gold. Every meter cubed is worth 1,000 liters. And there we go. So hopefully we match up with problem 3. If not, we were able to kind of see where we went wrong, get back on track. Okay, let's jump into 3B. Now you'll notice that I've gone through and just put on another version of that pool diagram because I really marked that last one up. So what question B is asking us for now is, if the liner in the pool needs to be replaced, how many meters squared would be required? So in case you were unfamiliar, the liner is that colored portion that covers all the surfaces of the base, the shell of that pool. So say this was an in-ground pool and I don't know, maybe it's made out of concrete. Then we're going to cover every part of that concrete base, the shell that holds the water. So for us to go through and do that, that means we need to know what every one of those surfaces are. Now, if I was to go through and tackle this one, then maybe we're breaking it up the same way. I don't know, I might be tempted to do this and maybe just go all the way across. Ooh, I don't like that line. And talk about this whole top portion as one big long box. And then we have this smaller portion as a box. And then we still have our triangular prism. So maybe we can see the 3 rectangles, I don't know. But not that you had to do that for this problem. Really what we need all of the faces. So what I'm going to try to do is I'm going to go through and I'm going to label everything as I'm finding it. Now, because these labels are going to get a little complex, I'm going to have to erase some labels as we go.
We'll do our best to work our way through that diagram. So let's take the first one that's probably the easiest. That wall in the deep end. Well, that wall is going to be a rectangle, and it is 5 by 3. Okay, now I just keep going. So I'm going to add to that. Well, now I need to do maybe the bottom of the pool. Like I have the very bottom of the deep end. That would be 5 by 3. Okay, now maybe I have this big tall rectangle here. And to speed some things up, I noticed that that blue rectangle has a matching rectangle on the opposite side of the pool. That is, those two sides are going to be the exact same size. So to speed some things up then, I could say that I have 2 of those rectangles. And those rectangles are 3 by 3. Okay, that takes care of all of the deep end. So I'm going to go through and just put on that that is the deep end. You clearly would not have to label that as part of your solution. I'm doing that so we can keep everything straight for our solution. Okay, let's keep it going. So I'm going to add to that. Well, now, maybe what I deal with is I deal with the shallow end. And so I'm going to have this rectangle right here, and it will have its matching part on the opposite side. Now, the only issue with that is that if I choose to break it up that way, then I'm going to be stuck with this side piece that I'm just going to label in green, because I would still have this remaining green side of the pool that I haven't filled with liner, or covered with liner, I should say. And although that is a trapezoid, and it's not really that irregular of a shape, it's not one that we know the formula for off the top of our head, or at least not likely. So, rather than just stopping that purple side at the end of the shallow end, what I'm going to do is I'm going to extend that all the way out, just as we did on the last problem. Because now my remaining side, as we go on that slope from the shallow end to the deep end, would be just a triangle. And that is a regular shape, and I know the formula for that shape. So let's look at those dimensions. And we did find in the previous problem that that dimension was 2 and that dimension was 2. So if we look at the purple, we're going to have that rectangle and its matching partner on the other side of the pool. So we're going to have 2 of those rectangles that are 6 by 1. Now, while we're there, we might as well deal with the 2 green triangles. So what we're going to have in that case is going to be 2 of our triangles. And our triangles are base times height divided by 2. Okay, that gets us almost there. I'm just going to erase on that diagram those 2 parts, because now I should be able to color in the rest. We need to get this wall in the shallow area. We need to get the floor of the shallow area. And we need to get the slope all the way down to the deep end. The nice part is all 3 of those are rectangles. They're just rectangles of different sizes. So let's add on the wall, the green wall in the shallow end. That is a rectangle that is 5 by 1. The floor of the shallow end is a rectangle that is 4 by 5. And I'm really running out of room over there. Now we got to come in on that red rectangle. Well, one of the dimensions is nice. We know that its width is 5, but we don't know what that length is. However, maybe we can see that we could calculate the length of that. The reason for it, I'm just going to erase a lot of that red, is because we found that that is really the hypotenuse of a 2 by 2 right triangle. And so maybe what we need to do is we need to hop out of that solution, because we have to go on the hunt and find out the length of that hypotenuse. And I'll just call it C. So we know that C squared is equal to A squared plus B squared. So C squared is going to equal 4 plus 4. C squared is going to equal 8. That means C equals the square root of 8. And we get an approximate of 2.83 meters. So now that we have that, then we can hop back in and we can add to the end of that the area of that red rectangle, which has a length of 5 and a width of 2.83 meters. Okay, I think we got every part of that pool now. Our job, let's go through and add everything up. So I'm just going to come over a little wider to give myself some room. We can calculate our 15 plus our 15. We now have 3 times 3 is 9, double it. We have 6 times 1 times 2. We now have 2 times 2 is 4, divide by 2 is 2, multiply by 2 is 4. 5 times 1, 4 times 5, and the last one we're going to have to do a little bit of work on. So we're going to have to calculate 5 times 2.83, and that's going to get us 14.15. Okay, our job now, let's add all that stuff up. So if we take everything and we add it up, then we should get up to a whopping 103.15. Now the question says how many meters squared would be required, and maybe we can buy part of a roll of liner. I have no idea how liner's sold. Let's put on our units, and we should be good. And there we go. That one had a lot to it. Okay, hopefully everything matched up with that, and we felt pretty comfortable with it. Now your job is to jump in and play around with all these composite 3D shapes. Okay, good luck.